In this video, we'll demonstrate how to apply auditory and visual analysis techniques to identify ion cyclotron wavestorm events in Audified solar wind turbulence. We'll be working with magnetometer data from the WIND spacecraft. This type of dataset allows us to investigate the solar magnetic field and to explore the microphysics of the solar wind. For example, we can investigate the interactions between waves and particles. This type of interaction is a fundamental process through which energy in plasmas is transported and dissipated, and ion cyclotron waves are traditionally identified by experts through basic visualizations and software platforms such as MATLAB and IDL. In this tutorial, we'll be using audio restoration software to navigate Audified solar wind data and identify ion cyclotron wavestorm events within the spectrum of the audio. For now, you can just watch and listen as we walk through several examples, and after the video is complete, you'll have time to import the audio files into iZotope and do some exploring on your own. We'll be using the spectrogram settings that we applied earlier in this tutorial series, which are displayed here. And we'll be focusing on the spectrogram instead of the audio waveform, so we'll click and drag this slider all the way to the right. First, let's take a look at a spectral representation of generic solar wind turbulence. The units on our x-axis correspond to data samples gathered over time. Thus, the left side of the spectrogram corresponds to the beginning of the data file, and the right side corresponds to the end. Time will always be presented in this way, from left to right. The y-axis displays the frequency spectrum of the solar wind turbulence from low to high. Our color map is displayed in decibel units, where 0 dB indicates the highest intensity, represented by white, and 115 dB down from this maximum value is shaded in black. Taking a look at our Audified solar wind spectrum, we can see that the lower frequencies generally contain more spectral power, as the bottom portion of the spectrogram contains a band of white, which fades through pink, red, yellow, green, and blue as we move upward. We can also see that the spectrum varies largely over time. Specifically, notice how the regions of red coloration extend upwards to various heights. Now let's have a listen to what this region sounds like. Note that while some regions are a bit louder than others, the entire audio file contains what is essentially unremarkable noise. Now when we have multiple files open in iZotope, they'll display in different tabs along the top. So here I'm going to click over to the second tab and pull up our second example, which contains samples gathered on the 27th of October 2005. Notice how in this example, we do not see a smooth gradient from white to green as we move from bottom to top. Rather, we see a thick band of red and white between approximately 300 Hz and 1500 Hz. This is an extremely clear example of an ion cyclotron wave storm. If we wanted to mark this within our file, we could simply highlight the region, click View from the File menu, then scroll down to Markers and Regions, and click Add. We'll name this event ICWS, which is an abbreviation for Ion Cyclotron Wavestorm. We can now see this region has been added to our audio file. While this example is quite pronounced, such bursts of wave activity are often short-lived and difficult to find through traditional analysis methods, particularly considering the large volume of available high-resolution data. Through audification, it has been found that many ion cyclotron wavestorm events have a distinct auditory character above the turbulent background. Let's have a listen now. You may have noticed a brief moment of silence during the second half of the event. This was caused by a small data gap and should be ignored, though it may be instructive to revisit this example later to familiarize yourself with what a small data gap sounds like. Now let's take a look at another example. Here we have data samples gathered on the 5th of September 2005. First, scan through by eye and see if you can pick out the region of ion cyclotron wavestorm activity. Where might you mark this region? The region in this file occurs here. Notice that once again, we see a band of increased spectral power in the mid-frequencies, though now the region of ion cyclotron wavestorm activity is embedded directly in the surrounding solar wind turbulence and does not stand out quite as distinctly as in the previous example. Let's hear what this sounds like. There are many different terms that could be used to describe the type of sound that you're hearing, but rather than providing some for you, try to think of your own as we listen through again. How might you describe what you're hearing in words? Now that you're starting to gain a sense for what this wave activity looks and sounds like, let's pull up our last example. This extended region contains data from the 29th of April, 2006. Scan through by eye and see if you can pick out regions of ion cyclotron wavestorm activity. Note that while the previous two examples were extremely broadband, it's possible that these waves may be present within a more narrow spectral bandwidth. That is to say, they may not stretch quite as far in the vertical direction. Also, the previous examples were extremely pronounced. It's possible that this type of activity may be present with a lower spectral power. The key thing to remember in this analysis is that we're looking for regions with an increase in spectral power in the mid-frequency range, specifically the range from approximately 300 Hz to 1500 Hz. Where would you mark the first region in this example? The first clear example occurs here, and we'll go ahead and add a new region. And let's have a listen to what this region sounds like. Now we'll listen through the rest of the file, and while we do, think about how you'd mark the rest of this example. And we'll listen through one more time. The activity isn't quite as clearly defined in the second half of the file, but we do begin to see a clear boost in mid-frequency activity around data sample 300,000. Here we see several red patches occurring between roughly 500 Hz and 1.2 kHz. It would be appropriate to select this entire section of the audio file and label it as containing ion cyclotron wavestorm activity, even though the activity is intermittent during this time period. Some examples that you'll find in the data may not have clearly defined boundaries, and in these instances, use your best judgment when labeling regions. Follow the instructions provided below to complete the final section of this tutorial series.